Okay, so last time we discussed the operation of a MOSFET. Here you have that VGS is greater than VTHN. Okay, that means you have just turned on the transistor, but there is no voltage between the source and the drain. There is no voltage, so you have reduced the barrier, so electrons can go up to the gate, the channel. The channel is created, but however there is no current flowing, because to flow the current you must have a voltage between the drain and the source. Okay? There is no voltage between the drain and the source, so it is on, but there is no current flowing. Then you have this situation where your VGS is greater than VTHN, that means it is on, and now you have applied a small voltage between the drain and the source. Okay? You apply a small voltage VDS, and that creates an energy barrier. This small barrier here to slide down like this. Slide down like this. As a result, the electron can then flow this way, drift along this way, and you will have a current flowing. Okay? So this, but in any case, both of them are operation in the triode region. Remember, we were discussing in the lab operation. This is also operation in the triode region. Operation in triode region or resistive region. Okay. That means in this case also VGS minus VTHN is, as long as it is less than or equal to VDS, VDS, it is in this region, or rather say as long as it is just less than VDS. Sorry, greater than VDS. This is triode region, greater than VDS. So if your VDS is 0 here, we didn't apply voltage. So if you apply 0 volts here, then of course this will be greater than this, isn't it? So it will be in triode region. Or you apply a small voltage, and still your VGS minus VTHN will be smaller than VDS. Sorry, greater than VDS. Must be greater than VDS. Greater than VDS. Okay. So if you apply no VDS and you apply a voltage between the gate and source, which is greater than threshold voltage, then it will go on, of course, and it will go on in the triode region because it is greater than VDS, which is 0. Again here, if you apply a voltage between drain and source, which is smaller than VGS minus VTHN, then it will still be in the triode region, Okay, still in this region, although you have a small current flowing. Okay, so you can actually operate also in another region which we discussed in the lab, which is called what? What is the other region we talked about? Saturation region. Okay. So this is how it works. This is triode region. You can have a flat band and electrons are in the channel but no flow. Just in the triode region. And you can also have something like this where you have a small voltage drop between drain and source and a small current flowing. Both are in the triode region. So in that case, in this case, is there a voltage drop here between source and drain? 0 voltage drop. Here between source and drain, a small voltage drop. What happens if you apply a larger VDS? Okay, where the VDS is equal to or greater than. So you could have a situation where VDS, okay, drain to source voltage is greater than or equal to VGS minus VTHN. This is the another case, the final case. In this case, you call it to be in saturation. So if the equality sign holds, then it is at the edge of saturation. If it is greater, then it is deep into saturation. The greater VDS compared to VGS minus VTH, the more and more it will be in saturation. Okay, the more and more it will be in saturation. So we can draw another diagram like this. So instead of drawing a diagram with charges, I'll try to make it very simple to save time. Just a simple diagram where you have VDS larger than VGS minus VTH or equal to. So this is again your transistor. This is your N plus diffusion. This is another of your N plus diffusion. Okay. This is your gate. This is your source. This is your drain. Okay. And this is your P plus body. Okay. And this is your substrate. So this is a P-type substrate. I can see a lot of people missing. Where are they? Where is Gulati? Gulati, that guy? You're here. Where is, what is the name of this guy? Kangonkor or something, Sure, yeah, where is he? Just send him a text. Tell him I'm looking for him. Where is Avi? Avi? No, Avi, yeah. Send him a text also. I'll pay for your text. How much? 20 cents? It doesn't cost much anymore, so doesn't matter. So this one is a P-type substrate and body source. So you can ground it like we did. We ground the body. Then we ground the source. Okay. Then between the gate and source we apply a voltage, which is your VGS. Then between the source and drain we apply voltage. Okay. We apply voltage here, which is VDS. And this VDS is say greater than VGS minus VTH. Larger than that, and of course here it is 0. Okay, then how will it happen? I'll just do it very quickly. So VDS will have now, VDS will have two parts. One is VDS equal to two parts. One is VGS minus VTH and one part, because it's larger than VGS minus VTH, plus one delta VDS. Something on top of this, isn't it? So you are saying that VDS now, the drain to source voltage, is greater than VGS minus VTH. That means it will consist of two parts, this part plus this part. Okay. So how will now, so last time we said the VDS drops between here and here. Now you have two parts. How will they drop across the channel? Okay. So here you can see the small VDS dropped from the source here, from the source edge to the drain edge. Okay. And it is small. But when it is large, how will it drop, That's the next question. So this is how it will drop. So you can do almost the same thing here. Okay, so our diagram will start from here. Put it down. Okay, our diagram will start from here. So you have, okay, so this will be up to here, Then we'll have two parts. So you'll have a channel. Channel actually happens, the channel tapers off, Channel will not go all the way, When you have VGS minus VTH, smaller than VDS, then the channel will not go all the way. Channel will taper off somewhere here. It will not go all the way up to the drain. So if the VGS minus VTH is just equal to VDS, if this equal to holds, then this channel will go up to here. As we increase the VDS greater than VGS plus VTH, more and more the channel will gradually move away. Channel can move up to here. That means that region of electron under the gate will gradually retreat, subside. Like a river, no flowing water, something like that. Then you might imagine, you might think, if there's no channel, how does the current still flow? That's the first question the student usually wonders. If there's no channel, how does the current flow? Have you thought about that? Because the channel, you see, will taper off here. The electrons are coming from here, taper off here, and how does the electron from here reach here? Do they fly, or do they? What happens? Huh? Is that wonder you? Is that something to wonder? Huh? Jen? Do you wish to ask me this question, or do you think you want to ignore this question?
Will it be on the test?
I'm testing you now. This is a test.
Then yes, if I'd like to know.
Every hour, every moment in life is a test. Just doesn't have to be one single 3 hour, Every day you are being tested, you see. You drive, you're tested, whether you're driving in the wrong direction or not. You're on test all the time. So, I'll answer the question. Of course you want to know. Let me try. So, this one here, and then you will have, what will happen is that you draw this line and draw another line here. So, there will be one part here, one part here, one part here, one part here. There will be 4 parts in your diagram. So, this will go here, and then up to here. Of course, there is a small barrier, and you go down like this, up to here. The small barrier goes up, and the same gap, okay, 1 point here, 1 point here. It's very difficult to draw this, okay. So this goes up and goes away down like this, up to here, reach up to here. And then what will happen? You have another line here. So you have one region, this is from this edge. This is from this edge. We reduce the source, then this will align with this. So I can actually make in here. This is your glass source, okay, and this is your channel still. This is your channel. Okay, so from here, from this edge of the source, it is going down up to here, and then this little part here is going to go down faster, Okay, the same gap. Same gap. So this is your 1.1 electron volt. This is 1.1 electron volt. Okay, and then you will have your this small bend here, this small bend here, and then this goes straight like this, on the end. So there plus drain. So this is your EC, this is your EV. All the way from here to here to here to here. Okay? So this is what's going on. So you'll have electrons here, which will roll over on this. Okay? These are all electrons roll over because there is a slope to roll over, and then this will roll over faster, faster, and then you'll go down into the drain. So your source is here, your drain is here, and your channel is here, and this is your depletion region. No channel. So you can see, although you couldn't see how the current would flow from here, because the channel is taper off here, you couldn't see. But from this you can see that how the current flows now. Because you have, although you don't have any channel here, you have a depletion region where you have positive charge here and you have negative charge here. Okay, so that means there is a potential higher here compared to here. Potential is higher compared to here. This is negative charge and positive. So here the potential is higher, potential is lower. So this actually, when the electrons come here, electrons are attracted by the positive charge, so they cross over into that side. So electrons find a slope. When the electrons arrive here, they find a slope due to this depletion region. This produces a slope. Electrons find the slope and slopes down and goes into the drain. Does it explain it now? Is it clear how it actually continues to flow the current? Is it clear? So have you passed the test? Why not? Did you understand what I said?
I think so.
Because you see, this diagram makes very easy. See, so here you have this positive charge, negative depletion region, because this is p-type, you have negative charge, n-type, positive charge. So that actually creates lines of electric field this way. This is the lines of electric field. The direction of the electron is opposite the lines of electric field. So electrons want to go the other way. Okay, electrons go to other way. So this is by charge diagram and this is by energy diagram. So electrons wants to go down this way. So you have continues to flow current. So actually this is really some resemblance with hydrology, the flow of water in a river. You see the river, and if you see the flow of water in a river slows down, what do they do? You know, if the flow of water in a river slows down, what do they do? No, if the water is flowing in river and the river becomes slow in navigation, you know, it loses its navigability. It loses it has to be rejuvenated. How is the river rejuvenated? You know?
More water.
Huh?
More water.
No.
Dam.
Dredging. You heard of dredging? Dredging. What is the fundamental principle here? You see, this is very important. The fundamental principle is that what you do is that here is that you create a potential energy. You see, the electrons when they come here, they see a lot of potential energy. You see, because of this of the height. As the electrons flow along this, they convert the potential energy into kinetic energy. The same thing happens in river. As the water slows down, you dredge the bottom of the river bed. You know, then suddenly the water coming here see a lot of potential energy compared to the level here, and then they run down the level, run down the riverbed level, and then they see what they do is that they convert the potential energy into kinetic energy, and then you have a rejuvenated river, the water flowing faster. And this is the same thing. Electronics with hydraulics have a lot of similarity, lots and lots. That's why you see in aircraft, all the controls used to be hydraulic. Now they convert into electronic, you know, because they are very similar. Okay. So this is saturation. Okay, this is saturation. And what does the curves look like, which we showed in the lab? Anybody can draw the current voltage characteristic curves for saturation and for triad region. Who can draw? Yeah, over there. Yeah, maybe you can draw over there. Yeah, draw nicely. Take your time. No rush. No. That is I. Yeah. ID. Yeah, one thing while you draw, you will realize yourself is that as you go for higher voltage, it will saturate later. It will, yeah. So it will saturate. The next one you draw will go farther up before it becomes angular. So it always, as you apply a larger gate to source voltage, it will saturate later. If you can make your lines a bit straighter, more linear, make it a little bit more linear. Yeah. No, you don't need that. You don't need the load line because don't have a circuit. You see, load line comes from the circuit. I don't have a circuit, so there's no load line. I only have a transistor. So you just draw the transistor characteristics. Okay. Very good. Okay, that will be enough. That will be enough. So you have, you see, so what is the name again? Kalam. So Kalam has nicely drawn the lines. So you can see this is VGS. So let me just improve on it a little bit. Okay. So you will have one axis here which is the ID, another axis which is the VGS, and here you have your ID, and you have your characteristic curves which is based on certain VGS. Okay. So as you go up and up, it will saturate later. You see here, the straight part is a triode region. This is like a resistance. Okay. And the other part is the flat part is your saturation. Okay. So you can see the farther you go, the higher the VGS, it will saturate later. You see, this is still triode region. This is still triode region. This is triode region. So as I draw in the lab, so you can draw a line like this where this is your triode region. And this is your saturation region. And what are these lines? What should I put here?
VGS1.
VGS, yes. VGS1, VGS2, VGS should be straight here, VGS3, VGS4, VGS5. Okay, there could be more. So this is one saturation, this is triode, and this is triode. Okay. So you can see here, if you look at the current voltage expression, you see, this is straight line. So if you look at this ID versus VDS, looks like a resistance, isn't it? Looks like ID versus like a, if you draw a resistance, okay, if you draw ID here, and if you draw VDS here, and draw a straight line, this looks like what? A resistance? ID versus like a resistance. So that's why you can also call it the resistive region. And this is saturated. You can see here the lines are straight. So you can also call it current source region. Okay. So that's the current source region. And you also have the resistive region. And there's different current voltage equations. So if you write the equation VD versus IDS, it will look like a resistance here, isn't it? So what does that equation look like? So what is the relation between VDS and ID when it is acting like a resistive region or like a triode? So that will be like a resistance. So what is that? Let's write it down. So in this region, where is this? In this region, ID equal to mu n. I won't derive the equation. I don't have time. So I'm just putting the equation. Mu n C oxide W by L VGS minus VTHN minus VDS by 2 into VDS. This is the expression for current, drain current to the VDS. Now you see here, you might ask me what is mu n, is mobility of electron, which you know. C oxide is the oxide capacitance. You might ask me what does it look like. W is the width of the channel, L is the length of channel. You might ask me what is the W, what is the L. So let's draw that. Okay. So if you actually draw a transistor in 3-dimensional, which I tried to do once in the lab, it will look like this. Okay. So I'm trying to draw it in the 3-dimension. So you will have your channel. Okay. So this is your oxide. Okay. And this is your source. And this is your drain. This is your channel length L, which is your channel length. And this is your W, which is the channel width, W. And C oxide is this capacitance. Between here and here, this is your C oxide. Oxide capacitance. This is per unit area. C oxide is oxide capacitance per unit area, but you don't have to know those details at this time. Are you writing? Right. What is difficult? You have to difficult writing? Is it? Yeah. I'm coming to simplification. I'll change to K. So you mu n C oxide WL, what we do is that there is a quantity comes which is mu n C oxide W by L divided by 2. This is called K. This is equal to K. So to simplify for our secondary level, we just call it K. Okay, and so this will become twice K. This will become twice K. Okay, this is VGS. Which one should I write again? Should I write this one or should I write this one? This one?
Yeah, that one.
I should write again?
I can't really.
Is it mu n over 2 times?
2, yeah. So it's mu n into C oxide into W
Yeah.
divided by 2 into L
Okay.
equal to K. So that whole thing we call K. Where is length? Length? Where's length? Where's length? Length is here. Length is not here. Okay, so now here you if you look at it carefully, if VDS is very small, you see, in this case we say that VDS is 0 or very small. If it's small, we can actually simplify it such that we can call ID equal to 2K into VGS minus VTHN into VDS. Okay. If it's very small, we can just neglect this. So you can say ID is approximately very close to equal to 2K VGS minus VTHN into VDS. Is it fine? Is it acceptable? Is it okay? Is it okay? ID equal to, I just remove the VDS by 2 because VDS is small. Okay, in the triad region. So now I can say that ID equal to approximately equal to, this is like a conductance G into VDS, or 1 upon G is your R, 1 upon G is your R, which is this slope, this resistance. And we can also call it RDS because we have the ID, we have VDS on this side, we have ID on this side, so I can call it VDS divided by ID equal to RDS, resistance between the drain and source in the triad region. Okay, the resistance between the drain and source. Between the drain and source here, the resistance between here, resistance of the channel equal to RDS. Okay, this is in the triad region. What is RDS in the saturation region? Can you tell me quickly? If the lines are so flat, what is RDS in the saturation region? Remember, VDS by IDS, what will be like here? RDS in saturation region will be like what? Small, large, very small, what?
Very small.
G may be very small. Conductance, I'm talking about resistance. VDS by IDS, you see. VDS, you see, VDS, if you change VDS by this much, you see the current small change only very little, you see. You change VDS by this much. How much the current change? Very little. So, this is what? In this region, you see, if you change VDS, so you take here, then draw a line like this, draw a line like this. So you go from, so this is VDS1, this is VDS2. You go from here to here on this line, and your current change how much? Very little, almost flat. This is the delta ID, current source region. That means, as you change the voltage, the current doesn't change that much. See? So this is like a current source with a large parallel impedance. So if you remember a current source, ideal current source, what is the ideal current source? Every current source will have a parallel impedance. So every current source will have a parallel resistance. So if the current source is ideal, then this is almost infinity. That means there is no current flow here. So in this case, you see here, this is like a current source, but there is small resistance. It's not an ideal current source. If it were an ideal current source, this line would be totally flat. In that case, RDS here will be infinity. So doesn't make undefined, more or less. Doesn't have any use. So when you say RDS, we really mean value of the resistance here in the triad region, which is useful information. Is it clear? RDS, because we will need it. What we are going to talk now next, operation of MOSFET as a switch will need the RDS. Okay, any questions? Is it totally clear that you have no questions? Is it so clear you don't have any questions, or you have questions? John? Is it clear? You came a little late, eh? Yeah. That's what happens. But you are smart, you can catch up. Anybody else? Kishka, any question?
No,
Perfectly clear? Emilia? Perfectly clear? Okay. Over there? Perfectly clear? Okay. So that means we understand what is RDS here, we understand what is RDS here, and we know the equation is like this. So it's like a, so if you model the MOSFET in the triad region, it will look like this. You will have a gate, you have a source, and you have a drain, and you have a resistance between the source and the drain, which is RDS equal to how much? Who can write it down? The RDS in this model equal to what? What is the expression? So if you had understood, you should be able to write it down. Who can do it? So I'm trying to make a model. So it's a DC model of MOSFET in triode. So this is like a resistance between drain and source. What is the equation for this resistance? Who is going to draw? Right. Equation is already there, and who can write it? I know, but what it is? Yeah, exactly. Yeah. 1 upon. You just remove the whole thing and write that 1 upon that. 1 upon G, yeah. So it's 1 upon G, exactly. VDS divided by ID will leave you this 1 upon this on the other side. Correct?
Okay.
VDS on the top, ID in the bottom.
Okay.
We'll take this on the other side, it will be 1 upon that. No, 1 upon. Okay, you write it down, then we'll put the 1 on top. N will be forgivable, if you don't have space. It's understood. Okay, very good. And put the equation here. Equal to here. Equal to. Put the equal to in front of the. Remove this. Put the equal to here. And remove this here. Thank you. So this is your model of MOSFET in triad region. Okay. So now what we're going to do is that we are going to move from this into operation of MOSFET as a switch. Operation of MOSFET as a switch. Okay, so now we're going to go to this topic. We know there's a saturation region, we know there's a triad region. Now we want to see how to operate the transistor as a switch The MOSFET as a switch. How to operate the MOSFET as amplifier? Yes.
Is there anything between the gate and source and network?
Nothing. You see, the gate is that's interesting. Gate and source is oxide. Usually at the frequency that we're talking, there's no current flowing. There's no gate current. So that's why it's vacant. That means the input impedance is infinity at low frequencies. So there's nothing there. So if you want to operate the MOSFET as a switch, would you operate here or would you operate here? Exactly, everybody knows that. It's almost similar. So we'll operate in the triad region because when you turn on a switch, do you desire any voltage drop across the switch? You don't want. So the only way you can get that, you operate here. If you switch is here, no good, All the voltage is dropping across the switch, then you have nothing to drop across your actual device, actual appliance. So you have to operate in the triad region. So now the big question is, how do you do it? When we were doing BJT, it was very easy. We just draw a load line, we see where the IC is at, We draw what is the bottom VCC at off, and then draw a line, okay? And that will give you idea of load line. And then we know that if we use a beta, which is very small, that will be beta of a saturated BJT, which will be, we said we pick 10 or 5 or 4 or 20, which will push the transistor into the saturation region. So we can solve the problem numerically. We can just find the IC set, divide by 10, get a base current, use that base current to determine the base resistance. Everybody remember that? That's the way we do. So you know how to do that part, BJT. What is the IC set? This is the IC set. You want what is the corresponding base current divided by beta set, 10, 15, whatever, so that it is ensured that it will be in that region. And then you find the base current, which will be large, find the resistance equivalent necessary to drive that current, which will be how much? Sometimes 10, 15 kilo ohm, And if you are getting 900 kilo ohm, that means you are not in the saturation region. You are in the forward active region of the BJT. That's indicator that you made a mistake, So never use the beta given for the BJT in your arithmetic to solve for the condition of a operation as a switch. So now, unfortunately, in MOSFET, there is no beta because there is no gate current. There is no current in the gate. Just now, he was asking me what is open. There is no gate current. IG equals 0. IG equals 0. So beta doesn't make any sense. It is a voltage-driven device. It is a voltage-driven device. It is driven by voltage. So you have to know in this case, for a given resistance in the drain, what is the gate voltage that will keep it in triad region. So no beta. You have to actually do it by the knowledge of the device. So if you're using a certain MOSFET to operate as a switch, then you have to know something about the switch, about the MOSFET. What current is produced in the triad region for what gate to source voltage. That you can use as a reference to determine whether your circuit, in your circuit, the MOSFET will work as a switch or not, for the load that you are trying to drive in the drain. So the problem is slightly different. But probably it is easier also in a way. You don't have to, your calculation may be reduced slightly. But even with the BJT, there was not a whole lot of calculation. So now we'll go to, before we go into saturation for transistor, for amplifier, we'll go into now operation of MOSFET as a switch. So to do that, we will not need these diagrams anymore. So we'll erase all of them. So these are all gone, gone, gone. Have you drawn this? Have you drawn this? Everybody? Have you drawn this? Okay. So this is the L and W. although we won't be needing it that much really. So we want to operate as a switch. For that again we have to go back to our ID versus VGS card. VDS, this is your VDS, this is your ID. Okay? Just 1 minute and then I'll give you the break. Okay? So you can draw your characteristic curves, So these are the characteristics from your device. So this is VG1, VGS1, VGS2, VGS3, VGS4, AS5. And what we will also do, we will draw a circuit, to operate it as a switch. Okay, just take your break now. 10 minutes.